If you've ever written a piece of code, you've probably had that moment of doubt, right? You ask yourself, is this thing actually fast enough?
It's a universal goal. But what does fast even mean? You know, if you try to answer the question, how many seconds does my function take to run? You've actually stumbled into a surprisingly tricky problem.
Okay, so to make this all a bit more real, let's use a super simple example. Let's imagine we have a function called findSum. All it does is take an array of numbers, loops through every single one, and adds them up. Pretty straightforward, right? We're going to keep coming back to this one.
So, why is that simple question, how many seconds, so tough? Well, the actual time it takes to run depends on a ton of stuff. Are you on a brand new MacBook or an old laptop? What programming language did you use? Heck, how many other apps do you have running in the background? The thing is, none of those variables have anything to do with how good your code is.
So let's just toss that old question out. We need a better one, and here it is. How does the runtime of our function change as the size of the input gets bigger and bigger? This shifts the focus from a specific number to a pattern of growth or scaling, and that is what really counts.
So instead of just talking about this growth, let's actually see what it looks like. I went ahead and ran our little findSum function a bunch of times with different sized inputs, and I timed every single run.
And check this out. Here are the results. Along the bottom, you've got the number of items in the array. We'll just call that n for short. And up the side, that's the time it took. And would you look at that? It's a nearly perfect straight line. As our input n gets bigger, the time it takes grows in a really predictable straight line way.
This kind of straight line pattern has a name. We call it linear time. It's one of the most common performance patterns you'll see. It just means if you double the input, you're pretty much going to double the time it takes to run. Simple as that.
Now, linear time is just one possibility. Imagine another function, one where the performance graph is just a completely flat horizontal line. No matter how huge the input n gets, 1,000, 1,000,000, 1,000,000,000, the time it takes never changes. That's called constant time. And let me tell you, that is incredibly efficient.
Then you've got the other end of the spectrum, the scary one. We call it quadratic time. Look at that graph. It's not a straight line. It's a curve that gets steeper and steeper. With this pattern, even a small increase in your input n can cause a massive, explosive increase in the runtime. This is the kind of thing that can bring servers to their knees.
Okay, so we've got these patterns, constant, linear, quadratic. But describing them with words all the time is kind of clumsy, right? As engineers, we need a clean, simple mathematical shorthand to talk about how our code scales. And that is exactly what Big O notation is. It's just a standardized way to put a label on these performance curves. So, constant time, that becomes O1. Linear time, that's ON. And that scary quadratic time, we call that ON squared. See how clean and simple that is? It's a universal language.
Now let's be realistic. You're not going to run experiments and plot graphs for every function you write. That would be insane. The great news is you don't have to. There's a shortcut to figure out the big O just by looking at the math behind it all.
Remember that straight line from our findSum experiment? Well, way back in algebra class, you probably learned that any straight line can be described by an equation that looks something like this. Time equals a times n plus b. Here a and b are just some random constant numbers that depend on your specific computer.
And this simple equation leads us to the magic trick. There's a dead simple two-step process to take any runtime formula and instantly convert it into Big O notation. Step 1. You find the single term that grows the fastest as n gets massive. Step 2. You just drop any constant numbers that are being multiplied by it.
So let's try it with our linear equation. We've got a times n and b. Which term grows when n grows? Well, a times n, obviously. B just stays the same. So that's our fastest growing term. Now for step 2, drop the coefficient, which is a. What are you left with? Just n. And that's it. The big O is O of n.
And this works even for more complicated formulas. Let's say we had one that looked like this. It has an n squared term, an n term, and a constant. Now think about what happens when n is like 1,000,000. That n squared term is going to be so gigantic, it makes the other two look like a rounding error. So we pick cn squared, we drop the coefficient c, and what do we get? Our big O, O of n squared.
Okay, that math shortcut is pretty neat, but we can do even better. Let's level up and see how we can skip the experiments and the formulas completely and find the big O just by reading the code itself.
Okay, check out this function. We'll call it constant function. It sets a variable to 0 and then it immediately returns it. It completely ignores its input. So, that first line, it's just one operation. It takes a constant amount of time. And the second line? Same thing. It doesn't matter if the input array has 1 item or a billion. This function does the exact same amount of work every time. Each line is O of 1, so the whole thing is O of 1.
Now, let's go back to our old friend, find sum. The first line, total equals 0. That's O of 1. The last line, return total, also O of 1. But the for loop, that's the heart of the function. That loop is going to run once for every single item in the array. So if there are n items in the array, the code inside that loop runs n times. The amount of work is directly proportional to n. And that's what makes the entire function O of n.
And this really gets to the core philosophy of Big O. We're not really concerned with what happens when n is small, like 10 or 50. Pretty much any code is fast enough for small inputs. We are interested in the worst-case scenario. What happens when n becomes absolutely massive? That's why the fastest growing term is the only thing that matters. It defines the long-term destiny of your function's performance.
So why do we actually care about this? What's the practical difference? Well, it's huge. An O1 algorithm is always going to be blazingly fast. Always. An ON algorithm? It's probably fine for a small list of items, but it could become a serious problem, a major bottleneck when you have to process millions of them. Knowing the Big O lets you predict these problems before they ever happen.
At the end of the day, Big O notation isn't some ivory tower academic concept. It's an incredibly powerful, practical tool for your daily work. It lets you compare two different ways to solve a problem and choose the one that's going to hold up when your application really starts to grow.
But, and this is a really important but, it's also crucial to keep some perspective. As this quote says, speed isn't everything. It's just one piece of the puzzle. You also have to think about things like, how easy is this code for my teammates to read and understand? And how much memory does it use? Sometimes a slightly slower algorithm that's much simpler is actually the better choice.
So, I'll leave you with a final thought to take away. Think about the most important, most critical piece of code that you're working on right now. Can you figure out its Big O? Because understanding how it scales, well, that's the first step to making it even better.